Okay, we'll get started, I guess. Hi everyone, I'm Dan Handley. I'm a firmware architect in ARM. Have a number of roles I look after or have technical authority over ARM's contributions to open source firmware projects and the trustedfirmware.org TSC chair. But here I'm also provide technical oversight of the ARM CCA reference software, and that's what I'll talk about today. It's something of a continuation of the talk I gave at Madrid last year, so I'll sort of skip over some of the details I talked about there, but there's one or two additional features or changes that have happened since then that I'll discuss a bit more. What else to say? There's loads of links in the slides, which obviously you can follow afterwards, but that will be done offline. I haven't got a huge amount of content, so if you've got any questions as we go along, any burning questions, feel free to interrupt me, and we'll try and handle that. We should have enough time to go through everything. Okay, let's get going. Just a quick reminder: ARM CCA builds on the ARM's CPU Realm Management Extension, and that's the hardware and the system architecture, the CPU and system architecture. And CCA is everything on top, so that's the software architecture standards that ARM produces on top of that, the reference firmware, any OS hypervisor enablement, and then finally at the top the additional services for example, for attestation and endorsement and things like that. I'll be mostly focusing on those second and third blobs from the top, yeah, if you've got any other questions outside of that, there's plenty of people in the room who know about all the other bits as well. So here's a stack diagram, which if you've been to any other CCA talks, you've probably seen before. There's a few more details I've put on here since last time. Obviously, the bits in kind of bluish color in this rendering, kind of all parts of the TCB, the Trusted Computing Base for ARM CCA, so the Realm guest VM itself, the stuff within there, and then what we call the CCA firmware, which is the RMM software, and there's a trusted firmware implementation of that, and then also the monitor firmware underneath, TFA as we traditionally call it. And then on the non-secure side is the host software, which is not trusted. The Linux KVM in our reference software could be another solution in other CCA deployments. And in our reference, we use the KVM tool VMM, but obviously Leo's coming after, and he can talk about the changes here in what's going on in Linaro in terms of QEMU support, the VMM and the emulation side. Some key interfaces here, which enable you to have very standardized and architectural software in here, which is key to the kind of CCA security guarantee. The RMI, the Realm Management Interface, is how the host controls the life cycle of Realm VMs and delegates memory into and out of those VMs. The Realm Services Interface is the interface from the Realm itself down into the firmware to things like measurement and attestation and getting data from attestation data from the system. And then finally the Realm Host well, not finally, actually I've added another one since I last did this. There's the Realm Host Interface, which is the interface from the Realm but back into the host. So obviously this is not trusted, the data that comes back from here, and that can either land in the host hypervisor or through into the VMM. And any interfaces between the host hypervisor and the VMM is kind of implementation defined. The final interface I've mentioned here is this FIRMI or firmware interfaces for Realm Management Extension specification. Patchin's in the room. He asked me to have a little mention of this because this is quite new. It's not available yet, but in the next, later this quarter, there should be an alpha version of that specification available. the reason that's interesting is because RME potentially can be used in other deployments, not necessarily fully conforming to ARM CCA, and it also allows better decoupling between some of these software components if you want to mix and match a bit better. Whereas currently the RMM and monitor implementation, for example, has a defined interface, but they're quite closely coupled with each other. So that's for things like standardized granular delegation between physical address spaces, and for IDE key management for the device assignment use cases. There's a couple more. I'll let Achin answer any additional questions on that. I think I've covered everything there. Yeah, so firmly expect later this quarter, I think maybe a beta towards the end of the year or early next year. I'll talk about the status of the other specifications as we go along. So where we are with CCA 1.0, when I say CCA 1.0, I mean the software for the RMM specification 1.0, which enables the basic protection of CPU state and memory content owned by a realm, which we consider the minimal viable product. The specification for that, the EA, or the REL, the final specification for that was in September last year, and there's TFA and RMM support for that has been upstream since October last year. The guest Linux patches were merged in January for this in 6.13. The host side patches have been going through quite a lot of rework. We're on V7, I think, is the latest from February. We're hoping that's going to land in the not too distant future in the next few months. And then there are combined guest host branches available there in the KVM tool patches, which should land shortly after the host patches do. Again, I'll say that, later I'm sure we'll talk about what's happening in QEMU land as well. The Realm guest firmware, which we use EDK2 for, there's the latest version 4 is targeting the EDK2 staging branch. That's been available since April. We hope that's going to land pretty soon as well. There's a couple of caveats there that it's subject to change because of these initial set of patches didn't standardize the way we do DMA addressing of shared memory. The top bit which splits the realm address space into kind of shared and private memory, that was masked in the stack when you pass through. But we realized that was going to be a problem for when we start to do real device assignment, and that bit needed to be passed through the stack, and so we've added some more standardization there. The guest Linux side is fairly minor changes, but in a number of components, and the guest Linux changes will be in V6.15. And then another change is around supporting larger host page sizes, so 64K pages in the host, and even though the underlying guest will still be 4K pages, now there's an interface to allow you to delegate memory in multiples of the host page sizes, and that will be coming soon. So how do you get it? If you deep into the development of the code, then shrink wraps are probably the best tool to use to get things working. You'll be able to get the latest versions of everything that all kind of work out of the box. And it also allows you to define overlay configurations to get more, dedicated specific stacks. For example, the last stable versions of various components, and then the tip of one of the components that you care about. That runs on our Arm's base fixed virtual platforms, and there is also integrated stack releases for that base FVP and our Neoverse V3 solution releases. Those Neoverse solution fixed virtual platforms have a more complete system architecture for CCA, some of the system IP available, and more CPU specific, microarchitecture modeling in there. And then finally, another way to consume this is by Arm's learning path to, if you're just trying to understand how Arm CCU works and accelerate that application development side of things. And there are a number of learning paths there. I've provided a link on the Arm developer website. I think about 6 different learning paths now available. So CCA 1.1, there's a number of use cases. 1.1, the partner feedback was that these are kind of essential for initial deployments, really. You know, the minimal viable product wasn't enough. I talked about some of these in Madrid, but I'll briefly just mention these. Memory encryption context is one, which allows each realm to be encrypted with its own unique key or tweak, rather than the entire realm physical address space encrypted with a single key. Planes is another one, which allows multiple privilege levels within a realm. They're kind of a lightweight, with lightweight switching between those privilege levels. They all share the same page tables, but with different overlays of memory protections. So the two use cases we're particularly interested in are being able to emulate a rich virtualization and device services. So, for example, using Microsoft's open HCL hypervisor, and so then you can have a lift and shift of your existing Linux and Windows workloads supporting various versions, and as I say, rich device services in there. The other use case might be to have a more enlightened stack that's specifically to support an enlightened guest Linux for essential security services like a virtual TPM and secure storage. And that enables you a much lighter weight hypervisor stack within that Planes environment. Live firmware activations in another specification is not strictly part of the CCA specification suite, but it has a relevance outside of CCA as well for other firmwares that you want to do hitless or rebootless firmware updates is the other terms you hear for it. The main use case here is being able to update your firmware without rebooting your entire machine, you know, keeping your cloud or server uptime as with minimal loss of availability as possible. The other use case outside of probably infrastructure deployments is to provide alternative firmware during boot with an image supplied by the OS itself. Obviously, that changes the trust model of, you know, from fundamental CCA, but that's important for example, client systems that are considering using RME. Something I haven't mentioned before is this flexible memory management. We were hoping to only address this kind of thing in the next version of the specification, but the late-breaking feedback from partners is that they really need to be able to do some optimizations in the system software to be able to dynamically allocate memory used by the CCA firmware itself, for example, for the level 1 GPT page tables or the granular objects in RMM, being able to dynamically allocate the memory for that rather than static carve-outs. And then the other use case is being able to do bulk operations for delegation of memory and creating stage 2 block mappings. The specification is actually not in the RMM spec yet. That should come in next month's version, and the beta version of that specification should be available, I think, at the end of this quarter. So that's a bit late, really, this feature coming. But yeah, we're still working on the software support for that as well. What else? I'm just going to talk a bit more about device assignment, because there are a number of sub-use cases within here which I just want to talk about. So I'll just do a quick recap. If you're interested in more detail here, I know Aaron went into this in much more detail yesterday in his RMM device assignment session. But essentially, you know, device assignment in this context is all about assignment of devices that conform to the PCIe TDISP flow, TDISP being the TEE device security protocol. And with this standardized, standardized architecture, it allows the realm to attest to the identify and configuration of a specific device function. So you start off in an unlocked state. The host puts into the lock state and deprivileges itself so it cannot access that device function, and that allows the realm to then go on request an attestation report for that device. And if it's satisfied that everything's okay, then you can go into the run state and start doing DMA. If there are any changes in the device configuration, that everything is kind of blocked from there on, and DMA access is revoked. And whether it's revoked or gracefully, releases access, then the device guarantees it will scrub any confidential state. And because it's standards-based, that means you don't need any device-specific knowledge in the RMM, which is kind of crucial to having a simplified RMM implementation. So with the number of use cases here, and that fundamentally is the top use case. We're trying to enable assignment of an off-chip PCIe device to a Realms TCB and grant DMA. But as well as that, we want to also be able to assign devices, on-chip devices connected to the root port complex, or so-called root complex integrated endpoints, whether that supports this SPDM TLS-like flow or not. And then finally, we also want to be able to support rekeying of the IDE, the integrity and data encryption link between the endpoint and the realm. DA coherent is all the remaining things are more advanced use cases. So DA coherent is about being able to assign TDI of a CXL or CHI device, like a device coherent memory, or a GPU connected via cache coherent interconnect. And so that's much more efficient in terms of memory sharing if your device supports that feature. But DA SMMU, probably should say DA SMMU level 1. Obviously, even for foundation DA, you need to support stage 2 isolation. But DA SMMU here refers to being able to support stage 1 isolation within the realm, so you can share workloads within a realm, can actually share access to that device function. ATS and again, PCIe defined interfaces for address translation and this page request interface. So ATS allows you to cache any translations and issue transactions that using the physical address from that translation. So you don't have to it reduces the number of lookups. And then the page request interface allows you to, the memory targeted by the ATS to be unpinned. If you don't have that feature, then you've got to pin memory during the use case, and so it's not as good for memory utilization. Finally, the P2P, peer-to-peer feature allows two PCIe devices to directly transfer data between each other without going via host memory, so obviously that's more performant if your device supports that. I'll come on to the roadmap soon. Another feature we're supporting, it's actually defined in the Realm host interface spec. The latest version is 1.0 Alpha 2, but we're looking to hit beta at the same time as the RMM spec 1.1. So these two specs are quite linked in terms of milestones. All these Realm host interface calls use an RSI host call as the transport, and then within that, they use a particular range in SMCC specification for function IDs. So you can use existing infrastructure in the host for passing those function calls through the system. And this enables early Realm guest firmware to establish an encrypted channel to the Realm owner's infrastructure to inject secrets. But the key thing is you can do this very early before the guest OS's networking stack is up and running. And then while this is happening, the host VMM can relay data to the Realm owner's infrastructure over TCP, and obviously that's ciphertext data. So the key use case we want to enable here is being able to inject the secure, the UEFI variable store, which includes the secure boot key database, and that allows you to then have a secure boot, UEFI secure boot within the Realm from a standardized guest firmware. And the Realm owner can decide what OSs are booted or disallowed. And so, the Realm owner is in charge there, and there's a decoupling between what the Realm owner wants and what the cloud infrastructure it has to provide. The other feature is just booting a standard Linux distro from an encrypted disk image. That's another use case we want to enable. So the advantage is here, you don't have this dependency on the cloud vendor's VM provisioning structure. They can just use a standard Realm firmware for any use case, and so takes the Realm, the cloud vendor out of the trust model there. So important thing to say here, although we expect this to be a really good solution and a good reference for many deployments, it's probably not standard. The cloud vendors may have their own ways of doing things, and it's going to maybe take a while to move to an architecture like this. So some CCA deployments may look significantly different to this, especially the first deployments. I think I should move on. I thought I would go a bit quicker than this. Software status, there is support in all the components for memory encryption context. That's been there since January. We expect the upstreaming for that to commence after the 1.0 host patches emerged. We don't see a big risk there. There's not a lot of complexity there, so upstreaming shouldn't be a big risk. For planes, there is an RMM work in progress branch being updated. We don't have a story for the plane zero, the most privileged plane stack hypervisor software yet. We've got some ideas of what that should look like, but that's not part of the reference stack story just yet. Hopefully by next time we'll have a better story there. Device assignment, there's an early drop of that, which Aaron mentioned yesterday, of all the various components. It's somewhat limited at the moment. It shows it's based on a slightly out-of-date RMM spec, the Alpha 12, the latest is Alpha 14, but it shows the SBDM session initialization and it provides an ABI for the root port programming, and it does the device attestation, but it doesn't do the SMMU and stage 2 programming to actually enable DMA access yet. Live firmware activation, there are some early framework packages in TFA available to demonstrate the live firmware activation of TFRMM, and we'll be working on update of TFRMM and secure partitions and the BL31, all kind of, there are different threads of activity all happening at the same time there. The boot sync patches should be available soon. It's been a bit on hold because of focusing on this 1.0 upstreaming, but that should be available soon. And the flexible memory management, we haven't quite worked out how and when we're going to deliver that yet. We need to see what the actual ABIs finally look like. Here's the roadmap. See a lot of stuff landing in H2 this year. The mech support, which should land upstream. The boot sync patches I just mentioned. The plane support, at least on the firmware side, should be ready by the end of the year. Planes host side as well, at least public branches available for that. The foundation RMM side of the should be functionally complete by the end of the year. Anything else to say here? And as I said, live firmware activation of the various components. I think BL31 actually is probably more likely early next year than this year, so need to change that there. And then H1 next year is kind of the completion of the foundation DA stuff, and then all the advanced DA use cases will be coming later on. The advanced DA use cases also somewhat depend on collaboration with external parties here, because there's a particular partner who's the only partner with hardware that supports some of these advanced features, so we're expecting them to do a lot of the heavy lifting there. Okay, I've managed to take much longer than I thought, so there's not as much time for questions as I thought, but happy to take anything. Now, I've just got a couple of resources for previous talks here. There's quite a collection of ARM CCA talks from Linaro events here, if you want any background of any of this. Thank you.